Next up, we have John ZuHone, who's going to be talking to us about astrophysical simulation analysis with YT, examples using galaxy cluster simulations, which I think is going to be very exciting. So, John, why don't you take it away?
Oh, thank you. So I'm hoping that there's a lot of pretty stuff to look at. So I'm going, my original plan actually was to give a talk where I walked through a bunch of code to show how one does analysis for this sort of thing. And then I saw what a lot of the way the other talks were going. And I thought, you know what, it's better actually to sort of tell the story. And, we can get to the code behind it, either in Slack or elsewhere. So my research is in galaxy clusters, and so let me motivate for those that maybe aren't familiar what galaxy clusters are. So these are the biggest gravitationally bound objects in the universe. So these are the things that are biggest things that gravity's holding them together. So we call them galaxy clusters because they were first noticed as groups of galaxies. And in this picture over here, I don't know if you can see my mouse, I guess not. In this picture over here, you can see most of the, fuzzy yellowish white blob things are galaxies. And then when they group together, we call them clusters. Now, most of what we call baryonic, and by baryonic, we just mean the stuff that makes us up, protons, neutrons, and electrons, mass is in the form of actually a very hot plasma. So these are just free electrons and protons and ions running around at like 1 million or so degrees or 10 million degrees, called the intercluster medium. And this is so hot that it emits X-rays, and that's what the pink stuff is in the image. It's a very hot gas, and it makes up most of what you might call the normal matter in the cluster. Most of the total mass in the cluster is in dark matter, shown in the blue, revealed by gravitational lensing, or the gravitational force, the warping of space-time is actually bending the light from distant galaxies behind the cluster. So that's kind of the motivation. And this is an image taken by the Chandra X-ray Observatory. So this is an image of the hot gas of the Perseus cluster, and the oddly shaped box on top of it is basically a representation of this other telescope that called Hitomi, which was launched in 2016, lived for a glorious 2 months, and then spun itself out of control and exploded, unfortunately. They're building a successor mission, which is almost identical, called XRISM. And the nice thing about Hitomi is that he was able to measure the motion of the gas in galaxy clusters. That's something that's actually very hard to do in X-rays. And you need a really sensitive instrument called a microcalorimeter for that. And what they're able to do is that they're able to show that the motions in this gas that you're seeing in the pearl picture were very gentle, not moving very fast compared to, say, the thermal motion of the gas. So the Mach numbers are just very, very small. This seemed very odd because at the very center of Perseus, there's a giant supermassive black hole that's blowing jets and bubbles into the cluster atmosphere. And the spiral-shaped feature that you can discern from the image it indicates gas motions. So some people suggested that this means that the cluster gas is very viscous. So whenever you try to stir things up, it gets damped out pretty quickly by the frictional forces in the gas. So what would that look like? Well, on the left, you're seeing a temperature slice of a simulation created in YT, or we're going to stir up the gas. And on the right, and on the left, you're going to see one where it's Inviscid, no viscosity, and on the right, you're going to see one with viscosity. We're going to stir it up by taking another cluster of galaxies, and we're going to pass it through. So what you can see is that you get these spiral-shaped motions, and in the Inviscid case, these interfaces here, these sharp differences in temperature that we create that are called cold fronts, these are sites where you develop a fluid instability called the Kevlin-Helmholtz instability, and so everything gets really ripped up and turbulent, whereas in the extremely viscous case on the right, everything is nice and smooth. And so some people were saying, well, maybe the gentle velocities in the Perseus cluster indicate that that we measure with Hitomi indicate that it's like the one on the right, perhaps. Maybe not that extreme, because that's actually pretty extreme, but something like that. But this is kind of tricky comparing the simulation to the observation, because how do we measure velocities? Well, we measure velocities using the Doppler effect. So what you're seeing here is a spectrum of the Perseus cluster taken by Hitomi. This big line here, that it's an emission line emitted by certain atomic transitions. This is a line that is measured very precisely by Hitomi, and by measuring where the line moves. So if it moves from the position you would expect it to be in the laboratory, it means that the Doppler effect has shifted the position of the line, and you can measure that shift to measure the velocity. But if you also measure the width of the line, so if the line is a bit, fatter than you would expect it to be in the laboratory, then this gives the velocity dispersion. In other words, what's the range of velocities? So we use this information to tell us what the velocities are. But the tricky part, of course, is that this in the simulations we can measure velocities using YT just by sort of grabbing the data in the simulation. We can do that in 3 dimensions. But in astronomy, when we measure the shift of a line, we're literally measuring the shift from all the velocities along the line of sight. The gas is what we call optically thin. So a photon just like gets emitted from a particle in the cluster and basically comes straight at us without being interrupted. And so you've actually got a bunch of motions superimposed, sort of tangled together. And so this is where YT comes in, like really, really handy to compare to the observations. So this slide has some math. Some of you are really excited. Some of you might be terrified. You don't really need to worry about the integrals here too much, but basically I just want to highlight that this is what a projection essentially is that we make a projection of, say, X-ray surface brightness or X-ray weighted temperature. And then the bottom 2 panels show the projection of the mean velocity and the velocity dispersion. So the mean velocity is is kind of like the position of that line that I was talking about, and then the velocity dispersion is kind of like the width of the line. And we can just sort of take the first and second moments of the velocity in a projection using YT, and we can get the maps of what we expect the velocity to look like, and just sort of make a first order comparison to what the Hitomi observation saw. So if we look at an Inviscid simulation, okay, so the map on the left shows you the velocity dispersion map, again, just by taking a moment map from YT. But then you say, but I know there's a lot of complicated structure in projection, so I want to get a sense of what that looks like. So what I'm doing is that that circle and that ellipse show you little cylindrical regions where I've literally taken it along the line of sight, basically along that direction that we're projecting on. And what you're seeing in the middle panels, with the different colors, the good old-fashioned YT algae color map. This paper is from a few years ago when that was still popular. These phase plots show you the velocity of gas on the y-axis and the direction along the cylinder along the z-axis. And so what you're seeing is that there's a lot of complex velocity structure in that top cylinder. It's just kind of a mess. You just kind of lots of gas randomly moving around. And in the bottom structure, we see that there's actually sort of a coherent, almost sinusoidal shape to the velocity as you're going down the barrel of that cylinder there. But then what happens when we take these velocity phase plots and we collapse them down to 1 dimension, okay? So we can't actually measure the structure along that line. We only get to see what it does to the effective emission line. So if you imagine that you just sort of take a single toy Gaussian emission line, which is that blue line, and then you fatten it up, move it around, smooth it around based on the velocity structure that you see from the simulation along the line of sight, the green lines are what you get. And if you look at this, this is a really big problem for interpreting the emission lines for the astronomers, because you can see you have two very different phase plots, distributions of velocity, and they basically produce the same shape of the emission line. So that's kind of interesting. Now let's take that very viscous simulation. And you can see that, there's not as much structure in the image on the left, the projection image. The small scale structure is gone because the viscosity is damped it out. You can see that there's a bit less structure, especially if I move back and forth in the phase plots. But what you can see is that the shape and the normalization of those green lines on the right has actually not changed very much. So either not viscous at all or very viscous, the line shapes, the line normalizations, the line widths are basically the same. So that's pretty interesting. But we want to make it even more realistic. So what we do is that we take this tool that I built on top of YT. It's called RHytHM. And what this does is that it actually creates simulated X-ray observations. So this is similar in vein or philosophy or whatever you want to call it to what Cameron showed us a couple of days ago with Trident. So basically you imagine that the circular thing on the right is a galaxy cluster, and then that little box is a resolution element with a volume and a density, a temperature, and a metallicity and a velocity, and that little element could be a cell, it could be an SPH particle or something like that. And then you imagine you've got a telescope over on the right, that's Chandra, that's measuring photons that's emitted from that. And so what RHytHM does is that it runs through all these resolution elements, and it creates these little simulated photons based on the emission we expect based on those properties. And then we can use the velocity of that resolution element to Doppler shift the photons, which is really crucial for this particular project. And then we have these simulated instruments. We'll go into all the details of that. We can make we can make a simulator for Chandra, or we can use somebody else's simulator for Chandra, or Hitomi in this case, and then we can make mock images and spectra. So here's some pretty pictures of some slice plots of density and temperature from YT, and then that's what a mock Chandra image looks like. You can see that there's gaps in the detector there and the Chandra image, and I've unfortunately placed the cluster in a really dumb spot where the very center is at the edges between the chips. So if I were a good observer, I would place it somewhere else, slightly off center. And then the right is a hypothetical, hopefully soon to be not hypothetical, who knows, instrument called Lynx, which would be a much bigger bucket to collect a lot more photons, which is why you see a lot more detail over there. But we can use these simulations to show what these different instruments would look like on the same source. And then RHytHM also produces spectra. So these are mock spectra produced from that simulation. These are the same sorts of products that you would measure using Hitomi of a real cluster. And so we can use to predict whether or not, by looking at the spectra, could you actually tell if the gas is viscous or not. So the punchline is that Hitomi cannot constrain the gas viscosity, and there's a really simple reason why. So there's a lot of stuff on these plots, but the top panels show the Inviscid and the Viscous simulations, and they just show the projection of that first moment of the velocity field using YT. So they're just projections. You just look at the sort of orangey purple map called the line shift. And you can see that the two projections, the top right panels, are very different, whereas Inviscid or Viscous. The Viscous simulation damps out a lot of that small scale structure. The problem is that if you look at the Hitomi maps on the bottom, the Hitomi resolution elements, the spatial resolution is very big compared to the resolution of the simulation. So these maps are actually created by measuring the spectrum in each of those 9 big cells and then fitting it to a model which tells us what the line shift and line width are. And so the problem is that if you had a telescope that had the spatial resolution of, say, YT up there, or Lynx, or potentially the Athena mission, which is a European mission, then you might be able to tell the difference between Inviscid and Viscous simulations. But the problem is that the differences are on just 2 small scales. So this is how you can use YT and simulated observations to actually tell you something about the physics and sort of connect directly with what the observers are looking at. So in the last few minutes of the talk, I want to talk about another application connecting simulations to observations. So these are real Chandra images of, there's 2 clusters there and there's a galaxy there, M87. But what's happened in these images is that we've actually taken the gradient of the image using the Gaussian gradient magnitude edge detectoring algorithm, which is actually developed, implemented rather, in SciPy. So basically, galaxy cluster images are noisy because we don't have the liberty of having like tons of photons. I work for Chandra, and so when Chandra is taking data, you can literally watch the photons coming in one by one sometimes for really faint sources. And so what you tend to want to do to sort of improve the look of your image is that you smooth it with a Gaussian. That's that G star I there, which is the convolution operation. And then you just take the gradient of that, which, numerically you can do a finite difference or something more sophisticated. And then you take the, since that's a vector, you take the magnitude of that, and that gives you these beautiful images. And what these images are showing you is they're showing you the edges. So in the Perseus edge image, you see bubbles near the center. Those are like the small scale circles. Those are actually bubbles blown by the supermassive black hole. And then you see a spiral shape, which are the cold fronts. And there's other cool stuff in all these images that I wish I could talk about, but I can't. But my collaborator, Stephen Walker at the University of Alabama at Huntsville, discovered that there was a funny looking bay shape in sort of the lower left of this Chandra image. And this is just sort of a random Science News or some other website type article that showed up that tries to make it really, really exciting. Scientists find giant wave rolling through the Perseus galaxy cluster. So Stephen thought this was an example of the Kelvin-Helmholtz instability, which I showed in those movies earlier on in the talk. And so he wanted to compare it to some simulations. He said, "You've got some simulations, how can I look at them?" So, and he also wanted to analyze this data in the same way as the observed data. So what observers typically have when it comes to astronomical images, they have this file format called FITS, which basically can store images and tables. And one of the things I wrote into YT a number of years ago was these FITS file writing capabilities, where you can write FITS images from like slices and projections. And so here's a really simple example of taking a data set that's part of the YT test data sets. It's a cluster data set, kind of like the ones I've been showing you. There's a function, a class rather, called FITS projection, which is which takes essentially the same types of arguments as a projection plot, except what it does is it returns this in-memory FITS object that you can then write to a FITS image. And then that thing on the right is this program called DS9, which has been around forever. And it's like one of the standard interactive programs for looking at FITS images. So that's a prediction of the temperature, which was created from YT. We've got some stuff in the docs to show you how to do this.
John, you have about 5 minutes left.
Okay, thanks. So I created a bunch of these images. So what the story should be is I created a bunch of images and I handed them off to Stephen and said, "Here, you should look." But in fact, one of the things I did a few years ago was I actually created a website to actually store hundreds of these images made from simulations. So I'm going to see how well this works. I'm going to drop out of the talk and I'm going to attempt to show the. So can everybody see the browser window now?
Yep, we can see it.
Okay. So this is the Galaxy Cluster Merger Catalog. It's in collaboration with some familiar folks. I think these icons need to be updated. Basically, this is hosted on the YT Hub, which if you don't know about it, is a great thing that the YT project is hosting, where you can host data for people to download and to browse into open Jupyter notebooks. And so we have all of these data, primarily FITS images that are hosted on the YT hub and then collected on the Galaxy Cluster Merger Catalog webpage. So here's an example of a web page where you can browse slices through the simulation. So here's a simulation of Galaxy Cluster. There's all these different epochs in the simulation. So these are, temperature, density slices. And then these are projections. So X-ray emission, temperature, total density, Compton Y, for those of you who are familiar with the SE effect. And then you can download, like my colleague Stephen, you can download the FITS files, and then he can perform the same kind of like Gaussian gradient magnitude stuff. And then there's even a browser-based version of DS9 called JS9. So if I want to open the FITS file, it'll jump down to this thing at the browser at the bottom. And then you can interactively sort of, look at the different FITS files. That's a terrible color map. You can look at the different FITS files interactively, and you can, move it around and zoom in and change the scale. So Stephen just kind of dove into this website, looked at a bunch of simulations, went to town on them. And I'm going to jump back very, very quickly to the talk as I finish up. So Stephen found some simulations that looked very, very like the observations. And he was able to actually make an estimate of what the magnetic field in Perseus probably is on the basis of the different simulations with different magnetic fields that he looked at. And to close out the talk, what I want to show you is that at the time when Stephen did all this, he worked for NASA, and NASA saw that this was getting a lot of play. And so the NASA Viz guys said, give us a bunch of your FITS images, and we're going to take the observations and the simulations, and we're going to make a really cool movie out of it. So I'm going to end the talk by hopefully being able to show this movie. Okay, and the NASA guys chose the funky music. So, okay, so that's it. And if there's any time, I'll take some questions.
That was awesome, John. I loved the video at the end, and I think the music was perfect. It felt very atmospheric. So,
Credit to the NASA Viz guys for putting that together. Francis Reddy, I think, was the guy's name that did most of that. So
Yeah, that was really, really cool. I think we can all be inspired by it for our future YT music videos that we've been discussing. Okay, so yeah, I think we have some time for some questions. So feel free to raise your hand in the chat if you have any. Looks like we've got one from Maxime.
Yeah, thanks a lot. I wholeheartedly agree that the video was amazing. Regarding the FITS files, I too tend to work a bit with observers when I can, and they do like FITS files. So how easy is it to produce these FITS files, and how easy is it for the observers to just observe, like use them without your input afterwards?
so basically, it can be as simple as this, what I'm showing on the screen, is that if you just want to show them an image, if you have a projection, you can make a FITS projection, and notice that I was able to pick the direction of the projection. You can also do an off-axis one. I was able to choose a width. I haven't done it here, but you can choose the resolution of an image. You can put several images into one file. There's a method to add sky coordinates. So if you can actually put it like at a place on the sky, and so they can kind of look at it in that same way. There are a lot of things you can do with them. It's, and there's a lot of, there's at the bottom, there's really good documentation. Now, of course, this produces a FITS image that doesn't have like noise or anything like that, right? It's just like a perfect from the simulation, but it's a good place to start. And, if you want to include more realistic effects, you have to build something like PyXM, or maybe you can like, make a noisy image yourself by manipulating the FITS file, using Astropy or something. But I would definitely check out the documentation. I don't know why I chose the dev URL at the bottom, but
I'm okay with it.
If you just Google YT writing FITS images, I think that should work. So
sounds good. Thanks.
Again, John, thank you so much for such a beautiful presentation. That was extremely cool.